Hello. In this section, we begin 4.4, Optimization Problems. In this lesson, we will cover optimization problems, and in a later lesson, we will cover more optimization problems. Let us begin. In optimization problems, we need to maximize or minimize some quantity. This is the problem of finding a local max or min. The max occurs where the first derivative is 0. A min occurs where the first derivative is 0. Here's an example. A rancher has a long stone wall and wants to use 2,400 feet of fencing to construct a rectangular pen along the wall as illustrated. What should x and y be to maximize the area in the pen? This is a classic calculus problem. This has probably been in every calculus book ever written, so why not? Why not us? Let's do this one also. Two things to notice. 2,400 is the only real number in this whole problem. 2,400 feet of fencing. We are constrained to have only 2,400 feet of fencing. The second thing to notice is what is the quantity that we are maximizing or minimizing? In this case, we are maximizing the area. So, two things that we're going to look at. One is the objective function. What is the object of our study? The object in this problem is to maximize area. So the objective function is the area, x times y, because x times y is my expression for area. But I also have a constraint. The x and y can't just be anything. X and y are constrained by this equation because there has to be 2,400 feet of fencing. So given this objective function and the constraint, I want to find those values of x and y that maximize the area. Here's our strategy. Find a of x. Take this objective function and express it as a function in only one variable, the variable x. Then solve a prime of x equals 0. Take that first derivative and figure out where is that first derivative equal to 0. Where the first derivative is equal to 0, that's where the function is maximized. Okay, let's give this a try. I have the objective function a equals xy and the constraint 2x plus y equals 2,400. Find a of x and solve a prime of x equals 0. So to find a of x, I'll need to take the objective function and express it in one variable, and the way we do that is by first looking at the constraint. Solve the constraint for one variable. In this case, the variable y is the easiest one to use. Sometimes for different problems it can be something different. So y equals 2,400 minus 2x. Next, use that to write the objective function in one variable. So a, now written a of x, is x times what used to be y, 2,400 minus 2x, and that simplifies to 2,400x minus 2x squared. Next, what is the derivative of a? Looks like it will be 2,400 minus 4x. Okay, so now let's solve where is a prime of x equals 0. So I just solve 2,400 minus 4x equals 0. I'll divide both sides by 4. 600 minus x equals 0. And there's the answer, x equals 600. So that tells me the value of x. X should be 600 in order to solve the problem. What about y? Well, to solve for the other variable, I can go back to my constraint, and I can see the constraint was solved for the other variable I need. So y equals 2,400 minus twice 600, and that answer is 1,200. So I found x, I found y, and that solves the problem. Those are the values of x and y that will maximize the area given 2,400 feet of fencing. Let's take a closer look at the function a of x. Our function was a of x was 2,400x minus 2x squared. When I actually graph that out, it's a parabola that opens downward, and it has a maximum point there Where is that max? That's exactly at the 600 that we found in the problem. And we found that by finding the derivative of a and setting that equal to 0. So that's a powerful technique. Let's take a look at another problem. Example 2, another rancher problem. Ranchers are always trying to optimize things. A rancher wants to build 2 identical rectangular pens sharing a common fence. The total enclosed area must be 600 feet. I see a number. Let me focus on that. What is the least amount of fencing needed to construct the pens? So least, this is a minimizing problem. Least amount of fencing. So the objective function is, what is the thing I want to optimize? In this case, I want to minimize amount of fencing, the total length of fencing. So maybe L is a good variable to use. And can you see that's 4x plus 3y because I have x, 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 and then y, y, y. So the total length of fencing that I need is 4x plus 3y. Well, my constraint, there's 600. What does that 600 mean? That's the total enclosed area. Can you see what that equation will be for the constraint? So the total enclosed area looks like y times 2x. Y times 2x, put the 2x over here, equals 600. And you can use this for our constraint, or if you want to just divide both sides by 2, we can end up with xy equals 300. I have the objective function, I have the constraint. Now let's take that objective function and write it in one variable. Well, I'll need to take my constraint and solve it for one of those variables. How about y equals 300 over x? Now I can make a function L of x, and here we have it. L of x is 4x plus 3 times what used to be y. Now it's the 300 over x. And that simplifies to 4x plus 900 over x. There's my objective function in a single variable. What am I going to do next? Take the derivative of L of x and solve for where it's equal to 0. Here's my derivative. The derivative of L is 4 minus 900 over x squared. Let's solve for where that equals 0. 4 minus 900 over x squared equals 0. Multiply both sides by x squared. 4x squared minus 900 equals 0. Divide both sides by 4. X squared minus 225 equals 0. I guess I can put the 225 on the other side and take the square root. And it looks like x equals 15. Well, then what is y? I can go back to where I solved the constraint for a single variable and find y. Y equals 300 over 15, which is 20. What did the problem really ask for? The problem asked for the least amount of fencing, so I still have a little bit more work to do. I know my x and I know my y. The least amount of fencing is given by 4x plus 3y. So the answer, 4 times 15 plus 3 times 20, looks like 60 plus 60, which is 120. So there's the answer to the problem. 120 is the least amount of fencing needed to construct 2 pens side by side where the total enclosed area must be 600. Give these problems a try, see what you can do. Really focus on the objective function and the constraint, being careful to identify those every time. All right, go to it.